Hello, welcome to another episode of Mystery Science. Today is the second part of our revision session on motion. Today we're going to be looking at forces, the combination of forces and moments. Last video we looked at the difference between velocity and speed, scalars, vectors, acceleration, motion graphs, and we looked at Newton's laws of motion. If you want to have a quick skip back through that video, please do so and then come back to this one and carry on where we left off. On Friday, I'm going to be releasing the third part of this revision series, and we're going to be looking at the motion equations, the Suvat equations, and we're going to be looking at projectiles. Then there'll be a further couple of videos on energy, conservation of energy, gravitational potential, kinetic energies. These are still in the motion topic, work and power, and then we'll have a special look at momentum, and we'll revisit Newton's laws in that video as well. So join us for this revision topic. Grab a pen and paper to make notes if you want to. I will be referring to questions in the textbook. If you don't have the textbook, don't worry. In the next couple of videos, I will be going through all the questions and how to answer them as well. All right, so let's start by talking about balance of forces and force diagrams and reminding ourselves of basic forces and how to combine forces. And then we're going to take them a bit further from GCSE. At GCSE, our forces were in straight lines. They were all on one dimension. And in A-level, we can start to look at it in 2 and 3 dimensions, as you can see in other videos. Before we begin, let's remind ourselves what we mean by gravitational field strength. In some of our other videos, we've been looking at fields and what they are, and I just want to remind you of that in terms of gravitational field strength. So we denote this with a small g, and it's measured in newtons per kilogram. Now these units should start telling you what the gravitational field strength actually is. Remember, we have a force due to gravity, which is our weight, and we have a mass of an object. So the gravitational field strength is given as the gravitational force per each kilogram of mass. Okay? So this is G equals F gravity over mass. F gravity, force due to gravity, is simply the weight. So now we have the gravitational field strength given as weight divided by mass. Obviously, we can rearrange that to weight equals mass times gravity, where the weight is in newtons because it is a force. Now we know little g as the acceleration due to gravity, but what it actually is the gravitational field strength. All right, let's think about different planets. Now we know this is year 8 stuff, so let's have a quick recap. The mass of an object doesn't change. The mass is how much matter there is in an object measured in kilograms. The weight depends on the gravitational field strength. If you're on Jupiter, gravitational field strength is completely different to the one on Earth. There we go. So on Earth, our gravitational field strength is given as 9.81 newtons per kilogram. We're used to using 10. We use little g as 10 at GCSE and Key Stage 3, but in A-level we use closer to the real approximation of 9.81. If we were to estimate the weight of an object, we would use 10 newtons per kilogram. This is the old Key Stage 3 and the GCSE equivalent. All right, let's quickly remind ourselves what we mean by a force, and let's talk about some of the types of force that we're going to encounter in this lesson. The first one is a contact force. This is nice and easy. This is any force caused by contact between two surfaces. This is where atoms are compressed together and the electrostatic repulsion pushes them back apart again. And this gives us a force. This is the contact force. There are, of course, non-contact forces like gravity, but we're also going to look at here tension force. So this is where we have a string or a rubber band. The object is stretched, or there's a force applied at both ends, and it enters a state of tension. So this is where the attractive forces between the molecules increase because they're being pulled apart and they want to be close together. We have to think about the equilibrium, and this is where all of the forces, if you add them all up in all directions, they equal 0. So you have a resultant force or a net force of 0 newtons. There is absolutely no motion, or there is no change in motion. And this is Newton's first law. The object will remain at rest until acted upon by an external force, or will remain in a constant state of motion unless acted upon by an external force. And this means simply that the acceleration will be 0 meters per second per second. Right, let's have a look at this example. We've got two rock climbers. We've got one on the top of the rock and one still climbing up. The one at the top is helping the one that's still climbing by pulling him up. Now, normally at GCSE, we wouldn't be able to solve the tensile forces on this because it's simply not in a horizontal or vertical plane. So we have to consider the tensile force of the rope or whatever it is the climber is using to pull. We have to consider the contact force. That's the normal reaction force of the climber on the rock. Now this is perpendicular to the surface of the rock. And then the weight of the climbing body. So the lines of action we can see now are not all acting in a single plane. They're acting in different planes, and all of these forces act through the center of gravity of the climber. And that would be there. So this is the point on a body where we can say that weight appears to act. We know in the real world that if you have a very large box and if loaded, then the center of gravity is normally the center of the box. But if you put all the weight on one side and you leave the other side empty, then that moves the center of gravity. So we approximate where that center of gravity is. This means that we can resolve this into a free body diagram. And a free body force diagram is one where we don't consider anything other than the center of the mass. So all of a sudden it's not about a climber anymore. It's about a free body with forces acting upon it. So here we are. Here is our free body, and we've got some magnitudes now. There is an angle of 13 degrees between the free body and the tensile force. There's an angle of 54 degrees from the free body and the normal contact force, and that is a force of 700 newtons. And we have the weight of the free body. So if the climber is in equilibrium, all of these forces balance. The contact force and the tension and the weight all equal 0. There is no net force, otherwise he would be accelerating. We can visualize this. If we put all of these back into a triangle, it would create a nice closed path. If there was a gap in the triangle, there must be a resultant force, and that resultant force would be given by the gap in the triangle. So here we go. We've put that into a triangle. We know the angles. We've got 13 degrees, 54 degrees, and a force of 700 newtons. And so this means we've got a closed triangle. We can now calculate all the other forces on it using trigonometry. Or we can draw scale diagrams, or we can separate into the components and solve by component, by the horizontal and vertical components of everything. Or we can draw a parallelogram, and we're going to go through all of these methods one by one and show you how to resolve all the forces. Okay, so when we think about our force diagram, we have to think of our three forces. There is a tension that's acting along the linear object, so that's creating the tension. In our case, it's a rope from the climber to the man on top of the rock. The weight, that's always acting downwards towards the center of the earth. We normally always draw our free body diagrams with the weight acting downwards. And then there is a contact force that's normal to the surface, and that always acts towards the center of mass of the contacting body. Okay, there are many situations where we can use free body force diagrams. And here's just a few examples. The first one, if we think about the free body force diagram of a bubble as it moves through a liquid, we have the bubble of air trapped in a liquid. Here's our bubble of air. It's going to have some sort of upthrust. It's also going to have some sort of weight attached to it, and the liquid is going to try and resist the flow of the bubble. This is the drag. So we draw a free body diagram. If the bubble is of a gas less dense than the liquid, then the upthrust is going to be bigger than the weight and the drag added together, and your bubble is going to have a resultant force upwards. We can also think of a book at rest on a table. Here we have a mighty physics textbook sat on a table. You have a contact force with the book on the table. The table is pushing up on the book, and we have the weight of the book pushing back down. These will always be balanced, otherwise the laws of physics will be broken as you put something on a table and it collapses through the table. And then we can think of more complex theories as well. You can have a gymnast holding onto a bar. That bar is suspended in mid-air, and that's supported by 2 ropes attached to the ceiling. So this means now that you can have a free body object representing the gymnast. You have the weight of the gymnast pushing down, and you have the weight of the force of the tension of both ropes pulling it back up again. If we have an object in motion and there's no acceleration, so there's no overall force, we're going to have this kind of situation where forces are balanced, but there's going to be some sort of lift or upthrust or contact force depending on what the body is doing. There's going to be a drag or a friction force opposing the direction of motion, and there's going to be a thrust, which is the applied force pushing it in that direction, and then there's going to be some sort of weight or force of gravity trying to pull it towards the center of the Earth. And as it's in constant motion, all of these are going to be balanced, so every single arrow must be drawn to exactly the same size. Now, we can work out our resultant forces, or our net overall force, by using a parallelogram. The parallelogram rule simply states that the sum of the forces, represented in size and direction by adjacent sides of the parallelogram, is represented in size and direction by the diagonal of the parallelogram. That's a wordy thing to say, but here we go. We have 2 sides of a parallelogram. We have 2 forces acting in 2 different directions, one of 1 Newton, one of 2 Newtons. So we can think of this as adjacent sides of a parallelogram. If you complete the parallelogram and then connect the 2 opposing corners, then you have the resultant force. So this now gives you the resultant force, it gives you a direction, and it gives you a magnitude. So you can draw these to scale, and then the angle and size of the purple line there will give you exactly the size and direction of that force. So let's look at an example. If I have 3 weights attached to a pulley system, weight 1, weight 2 are attached at either end of a pulley, and weight 3 is suspended in between the 2 pulleys. Now, if we say that weight 1 is 7 newtons, weight 2 is 9 newtons, weight 3 is 8 newtons. The angle θ1 is 61.5 degrees, and that is the angle between weight 3 and the pulley that weight 1 is attached to. And angle 2, θ2, is given as 52.5 degrees. That's the angle between weight 3 and the pulley holding weight 2. Now, these are not in straight lines. You've got a weird situation where all of the weights, the forces, are acting downwards towards the center of the Earth. But if we consider the forces on weight 3, what's going to happen? Let's look at free body force diagram drawn to scale, and that would look like this. Because we're just focusing on weight 3, we're only interested in the tensile forces going off at 61.5 degrees and 52.5 degrees towards the pulleys. Now these forces are exactly the same as the forces of the weights W1 and W2. Okay. So this is what our scale diagram would look like. You'd typically draw a line representing your 8 newtons towards the ground. You would then draw 61.5 degrees from the normal. You would draw 7 centimeters representing 1 newton per centimeter, and then you draw 9 centimeters on the other side. And that's what the free body force diagram drawn to scale would look like. If we look at the same example with the parallelogram rule, we know that it's not moving. Therefore, weight 1 plus weight 2 plus weight 3 all equals 0 in vector form. Okay. So weight 3 is in the opposite direction to weights 1 and 2. Therefore, the vector sum of weight 1 and weight 2 minus vector W3 all equals 0. So weight 1 plus weight 2 equals weight 3. So we can do this by adding W1, W2 into a parallelogram, and this will give us W3. There's weight 1, there's weight 2. We know these angles, 61.5 and 52.5. We draw the rest of the parallelogram. There we go. Put those angles back in, and then we can simply connect the opposite edges, and this visualizes our weight 3. And if we draw on that to scale, we can actually measure weight 3. Okay. Now, it could be inaccurate because of slight errors in your drawing. And obviously this is compound errors because you can make errors on each part of that drawing. That's quite a lot of factors for the errors to rely on. Let's look at the same example drawn as a triangle. We draw each side of the triangle in the order in which the forces are added. So we think about weight 1, and that's going from the center of the normal to at 61.5 degrees. Then we add weight 2, which is then at 52.5 degrees, going in that direction. And so we connect the arrows together, and that's going to give us W3. Okay. Again, the errors are going to creep in due to the discrepancies in drawing scale diagrams. And it depends how good at scale diagrams you are. The worse you are, the bigger the error, the better you are, the smaller the error. But you still have those compound errors in measuring the angles, measuring the lines. And again, each angle and each line that you draw increases the number of errors that could creep in. And now let's look at the same example using trigonometry. And we're using the trigonometry to verify the forces. Remember, we know all 3 forces. They're 7, 9, and 8. So we're using this to just verify that we've got the correct answer. So if you have a look at this scale drawing, you have W1, 7 newtons, 61.5 degrees away from W3, which is 8 newtons, and W2 is 9 newtons at 52.5. And it says at the bottom that 1 centimeter is 2 newtons. Okay, so forces W1 and W2 are diagonal, whereas force W3 is vertical. So we want to resolve them into the same direction. So we look at the components. What we're trying to do is we're trying to find the components of the forces opposing W3. So we want to find the lengths of the 2 sides parallel to W3. So this means we're going to break down W1 into its horizontal and vertical components. We want the vertical component. Same with W2. So here we are. There's the vertical component that we want. And if we just look at W1 for a moment, we label the sides based on the known angle. We know the angle, 61.5. We know the hypotenuse. We know what we're calculating what the adjacent is, and we know the angle. So using the Sokotoa rule, or shouts of happiness come after having tankards of ale, we know the adjacent, and we know the we're trying to calculate the adjacent. We know the hypotenuse, so we can use cos of the angle to give us the adjacent. So cos 61.5 gives us the adjacent divided by 7, because remember a force is F cos theta in this example. So therefore 7 cos 61.5 will give me the magnitude of that adjacent. Now W2 is the same, just flipped, so we can use the same trigonometric rule, and that gives you 9 cos 52.5 gives you A. And this W1 plus W2 equals W3. So you add those together, 7 cos 61.5 plus 9 cos 52.5, and that gives you W3, which remember should be 8 newtons. It actually comes to about 8.8. So that's a 10% error based on this trigonometric ideal. All right, so let's look at this example here. This is a simple multiple choice question that you will find in any exam at the beginning. They give you some multiple choice questions. So a pilot wishes to fly due east. A wind is blowing in a northerly direction. The direction of north is as shown. Which of the following correctly shows the direction the plane should point? So let's look at all 4 options. Option A, if the plane has its thrust going into that direction, it's going to be enhanced by the wind in the northerly direction, and the plane's going to increase velocity in the northerly direction. It's not what he wants to go east. So if we look at B, where he's going due east, what's going to happen with the northerly wind is going to have an effect on the aircraft. It's going to add a force, and so the aircraft is going to drift off to the northeast at some magnitude, and that's not what the pilot wants either. And if you look at option C, he's already pointing to the northeast. That northerly wind is going to push him off even more to the north. So our only option really is option D. And this means that he can fly in a slightly southeasterly direction, and the northerly wind is going to push him back towards a true east direction. Okay, so that was adding forces together in vector form. Let's have a quick look then at moments. Now this is the point of a lesson. I normally sit and hum Martine McCutcheon's "This Is My Moment" to myself, normally with students staring at me in horror, for A, because I'm singing, and B, because I have no idea what that song is. I'm not going to do that because I'll be slapped with some sort of copyright infringement and possibly locked up for insanity. So, what is a moment? A moment is effectively a turning force. It's a turning effect of a force. We think about a turning object, and we think about the forces of that object. A moment is the actual turning effect of that force. And it's a product of the force and the perpendicular distance between the axis of rotation and the line of action of the force. And this brings rise to the actions of levers and things like that, where the further you are away from the pivot point, you can apply a force, and that gives you a bigger moment, a bigger turning force, if you will, and that allows you to give extra force onto your pivot. So the moment is given by Fx, where x is the perpendicular distance. We measure this in Newton meters. It is a force multiplied by a distance. So let us quickly remind ourselves of the principle of moments. If something is going to be in equilibrium, the sum of the clockwise moments must equal the sum of the anti-clockwise moments. If you're trying to turn something in the clockwise direction, trying to turn something in an anti-clockwise direction at the same time, if the forces and the moments are all the same, then you have equilibrium. Nothing is moved. This is the point where we're going to go through this. If you're in a classroom with me, I would now hand you some sort of ridiculously hard moments puzzle, get you to work it out, and get you to work out the weight of a cat in a box, which is always one of my favorite things to get students occupied with. I might try and find that puzzle and link it down below. All right, so if you consider a scale or a set of balances, you have something finally on a pivot point. If you have 2 weights times 2 weights. Yes, a force of 2 newtons, 9 meters away from the pivot point. That gives you 18 newton meters. That's the moment. And then if you have 3 newtons, 6 meters away from the pivot, you've also got 18 newton meters. These things are going to balance. The other example I like to give are my children. My children are 6, 5, and 2. If I want to get them all on a seesaw, then you have to be able to work out the moments when it's perfectly balanced and who's going to do what. There's no point in my putting Angus, my 6-year-old, on a seesaw with Felix, my youngest, on the other end. Felix is not going to have much fun. He's going to be sat up in the air. Angus is going to be sat on the floor. So we have to balance it out. So how can we do that? What we can do is we can move Angus closer towards the center of the pivot, and that changes the moments, changes the force, and allows them to seesaw nicely. Okay, so as I've said, this is completely in equilibrium. The moments are balanced. This scale is not going to tip. In order for an object to tip and be in rotational equilibrium, you've got to have more moments on one side or the other. So to be in rotational equilibrium, the sum of the clockwise moments must equal the sum of the anti-clockwise moments. As I say, if you want it to move, to tip, to balance, to unbalance, you have to change one or the other. One of the moments has to be bigger than the other. Here is an example then. Let's look at 2 children sitting on a seesaw. We look at the seesaw, we're going to have 2 points, one 2.5 meters away from the pivot, one 2 meters away from the pivot. I've put a child of roughly 40 kilograms, 400 newtons on one side. How much can I put on the other side to balance this child? What is the force F? So if we think of this as a perpendicularly rotationally balanced seesaw, then the net forces must be 0. The sum of the clockwise moments must equal the sum of the anti-clockwise moments. Therefore, the anti-clockwise moment altogether is 400 newtons multiplied by 2.5 meters, and that gives 1,000 newton meters. The clockwise moment, because it's balanced, also has to be 1,000 newton meters. We know that's 2 meters away from the pivot, so the force F is going to be given as 1,000 divided by 2, which means that the force F is going to be 500 newtons. Let's put it in simple terms. Let's go back to pretending that the gravitational field strength is 10 for a moment. I've got a 40 kilogram child sat 2.5 meters away from the pivot. I can put a 50 kilogram child sat 2 meters away from the pivot. The beam itself has a moment of 0 because the perpendicular distance is 0. It's just sat on top of the pivot. Okay, so we're both in complete equilibrium. We've got 400 newtons on one side, 500 newtons on the other. All the forces acting on this are equal. The weight of the beam is 500 newtons. The contact force is 1400 newtons. The entire system is in equilibrium, as we've said, and the contact force is the complete weight of the beam, all pointing down onto the pivot. So the contact force of the pivot pushing back up is the entire weight of the whole system, 500 newtons plus 400 plus 500 newton weight of the beam. Right, so let's have a look at a bicycle. Here is our lovely bicycle. The bicycle itself has a weight of 80 newtons. The child sitting on the bicycle has a weight of 300 newtons. Imagine for a moment there are 2 contact points at the base of the tyres, point A and point B. Our reaction forces, force A and force B, reacting back up from the bicycle. So these would be the total weight of the child and the bicycle, which is 380 newtons. Force A and force B would share that load, so it would be half of 380, which would be 150 plus 40, 190 newtons at each point. We know that we're given that the points are 0.9 meters apart, and the child is 0.2 meters away from point B, and that point B and the center of mass of the bike is at 0.4 meters from point B. So let's take away the bike itself and let's look at just these three bodies. Okay, so we can calculate force A and force B. As I say, force A plus force B must be 380 newtons. Therefore, at pivot A, we look at these as two different pivots. The clockwise moment has to equal the anti-clockwise moment, otherwise there's going to be some rotation, and we don't have any, everything's at equilibrium. The clockwise forces are the weight of the bike and the weight of the child. The clockwise moment, therefore, is 80 newtons times half a meter, and that plus the 300 newtons plus 0.7 meters. The anti-clockwise forces, the anti-clockwise force is force B, the contact force on the back of the bike, and the anti-clockwise moment is force B multiplied by 0.9 meters away from that first pivot. So we calculate this because they are equal. Force B times 0.9 meters is equal to the moments that we've discussed earlier. So 80 times 0.5 plus 300 times 0.7 is equal to force B times 0.9 meters. So force B is 0.9. Force B times 0.9 is 250 newtons. And that gives force B given to 277.7 newtons. But let's look at the other side. Pivot B, the clockwise moment is equal to the anti-clockwise moment. Again, there is no rotation. Clockwise forces are force A. That's trying to force it clockwise. The anti-clockwise forces, therefore, are the weight of the bike, the weight of the child. I missed the concept of clockwise moment, sorry. Clockwise moment is force times 0.9. And so now our anti-clockwise moment is 0.4 times 80 newtons plus 0.2 times 300 newtons. And we work that all out. We know they're in equilibrium. Force A is 0.9 meters away, and that gives force A is 0.9 times 92 newtons. And so we have force A is 102.2 newtons. So we can see they are not evenly distributed, which makes sense as most of the weight is at the back of the bike. So force A plus force B equals 277.7 newtons plus 102.2 newtons, which gives us 379.9 newtons, which is a very close approximation to our 380. It shows us we have done something very right. Right, let's look at a wardrobe that is on a pivot. So we're going to be pushing a wardrobe with force P. We're pushing that in this direction. The wardrobe is 40 kilograms. Calculate force P. Now you'll be given some more dimensions. So for example, the height of the wardrobe is 1.6 meters. The weight is 40 kilograms. There's going to be a contact force on the pivots. And we know it's been tipped at 30 degrees. And the distance from the pivot to the center of mass is 12 centimeters. All right, so let's work this out then. We know it's not rotating, so the clockwise moment is equal to the anti-clockwise moment. The moment for weight is 12 centimeters away from the pivot point. So the perpendicular distance of P to pivot point is 1.6 meters. The weight of the wardrobe is 40 kilograms times 9.81, which gives you 392.4 newtons. So now we can work out our moments. The anti-clockwise moment is simply the weight of the wardrobe multiplied by the center of gravity distance from the pivot itself. So 392.4 newtons multiplied by 0.12 meters. The clockwise moment is P. We're trying to push it in that direction. So that's P times 1.6 meters. So P times 1.6 is equal to 392.4 times 0.12, which gives P as 29.43. Okay, knowing about moments tells us about stability of the objects. When the line of action of an object's weight is beyond the base, there's going to be a resultant moment on the object. As soon as there is a resultant moment on the object, we end up with a complete instability. So you start tipping this object. The center of mass there is behind the pivot point, so it's perfectly fine. But as soon as you tip it forward so that the center of mass is beyond the pivot point, this thing is going to come crashing down. So the object topples when the resultant moment about its turning point is not zero. We've just proved that. If it was perfectly balanced, where the center of mass would be directly over the pivot point, it would balance there forever. We know by practice that's incredibly difficult to achieve. A slight deviation on either side will cause a shift and a resultant moment. All right, those were fairly straightforward. Now, unfortunately, exam boards love to look at moments at an angle. And I'm going to go through the infamous basketball hoop question or netball hoop question that we've seen in a number of different exam papers, actually. But first, let's look at a basic one. I've seen this as well in exam papers. We have a shelf and it is attached to a wall and it has some sort of tensile force holding it up. So in this situation, we have D1 is the distance between, is the distance to the center of mass of the object. So the weight is there acting down from that distance. D2 being the distance of the entire shelf, or the length of the shelf. Now, weight times D1 does not equal F times D2 here, because the moments are measured over a perpendicular distance and we have a force at an angle. So weight times D1 has to be equal to the vertical component of the force V multiplied by D2. Okay, there we go, FV, so that's the vertical component of the force. And so we use trigonometry. So weight times D1 is F sine theta times D2. Okay, so you have D2 and the force. We can connect the line of action of the force to form a right angled triangle with the pivot, and this can help us out with this equation. There you go. We use the perpendicular component of D2, and so that you have a direct line of contact with the force. This helps us work out the angles of the forces. So here is our angle. The angle of the force from the perpendicular is equal to the angle of this triangle, basic rule of triangles. And so we know that the perpendicular the perpendicular size of D is D2 times sine theta. So the moment is simply F sine theta times D2. So weight times D1 is F sine theta times D2. So the moment of a force is the product of the force and the perpendicular distance between the axis of rotation and the line of action of the force. This allows us to resolve the forces in different directions. So the first thing you have to do is resolve all the forces into the same direction, perpendicular to the axis of the rotation, using the trigonometry. Now, here we go. Here's one example. We've got a car in a showroom and the car is on a slope. The center of mass is there. Its weight is 15,000 newtons. The incline is 20 degrees. And you have a tensile force 60 degrees away from the ramp, and you have a distance from one pivot to the next, the pivot to the center of mass of 1 meter, and then you have a distance from the centre of mass to the tensile force of 1.5 meters. So it tells you then you have to calculate the tension in the rope where the car is being towed. This one's being towed. Sometimes it's a tensile force holding up a ramp. And that's at 60 degrees. Right, there is no rotation, so again we know that the conservation of moments works. Clockwise moment is equal to the anti-clockwise moment. The clockwise force trying to drive it in a clockwise direction, is the same as the weight. The anti-clockwise force is the tension, so we can work out what the tension is. It's in rotational equilibrium, so we know that the tension is equal to 15,000 newtons, but only in the vertical plane. So there you go. So if we want to work out the tension, we can calculate the tension by knowing what the vertical component of the tension is. We know that this angle here is 20 degrees. This will give us the contact force, the normal force. And so we are looking for an adjacent, so we're going to use cos here. So we're going to use cos 20 to give us the weight. So 15,000 newtons times cos 20 is going to give us the normal force of 14,095 newtons. So this moment is going to be 14,095 newtons multiplied by 1 meter, because it's 1 meter away from the pivot. So that gives us again a moment of 14,095 newton meters. Quite simple. There we go. So this is our weight force pointing down in the plane. So what we've essentially done is we've rotated the plane so that we can now look at 60-degree angle from that tension. So we need to now look at the force perpendicular to the weight. Okay. We know that the perpendicular moment is the same as the perpendicular moment of the weight. So the moment of perpendicular, T perpendicular is going to be the full length, 1 meter plus 1.5 meters, and that's going to equal 14,095 newton meters. So now we have the tension in the perpendicular direction is going to be 5,638 newtons. There we go, that's the tension in that direction. We know that the angle here is 30 degrees. Okay. We know the opposite, and we're looking for the hypotenuse of this triangle now. So we're going to use sine. So 5,638 divided by sine 30 gives us the magnitude of the tension, which is 11,276 newtons. Okay, this is the notorious exam question of the netball hoop. We have seen this a couple of times, and it's been incredibly difficult to work through. And this, as I say, has appeared on exam papers, so is worth looking at. We're looking at a netball hoop. It has a base arrangement at the bottom. It has a post that holds it up. It has a board. You can tell if this is basketball or netball. It's got a board, so it must be a basketball hoop, but attached to the floor for some reason. So we've got it pivoted at an angle, and then it says, what is the minimum force of wind needed to topple the hoop? So we're now talking about causing the moments to imbalance. We have to work out all of the moments for equilibrium, and then we have to work out what that force of the wind could be to force an imbalance and therefore a toppling. Okay? And that's quite an interesting thing to realize. So we know that the hoop is going to be toppling, so we know the moments are going to be imbalanced. We're looking for the minimum force needed. So we're looking for the clockwise moments almost equal to the anti-clockwise moments, but not equal. So close that it's almost balanced, but not, because we're looking for the minimum force. So the sum of the clockwise moments is going to say equal the sum of the anti-clockwise moments, and then we're going to add a little bit more. So the clockwise moment is the weight of the base. The anti-clockwise moment is the force of the wind and the force of the post. All of these are acting at an angle, and this makes this incredibly difficult. So you've got to resolve all of these things at different times. So let's start with this one, the weight of the post and the backboard. You've now got to look at all of these are acting at an angle of 15 degrees to the normal, and so the weight of the base is acting at 15 degrees. So again, we're going to have to look for the perpendicular moment. So let's look at the base itself. We're going to work out the clockwise moment here. We know that the distance from the pivot to the center of mass of the base is 0.45 meters, and we know it's toppling by it's balanced at an angle of 15 degrees. We know that that is 870 newtons because we're told in the question that the weight of the base is 870 newtons. We have to work out the component. We know what the hypotenuse of this triangle is. We need the adjacent, so we're going to use cos. So we have cos 15 is equal to our adjacent divided by 870 newtons. So the adjacent is equal to cos 15 times 870, which gives our force of 840.355 newtons. So our moment is that the 840 times 0.355 multiplied by 0.45 meters, and that gives a moment of 378.16 Newton meters. That is our moment in the clockwise direction. What we've done is we've rotated our perspective somewhat to 15 degrees, and we're trying to think of the whole thing as a perpendicular arrangement. Now then, we also have to consider the post and the force of the wind. So the moment of the base we've now determined, 378.16. Let's have a look at the post arrangement. That is 27 newtons, acting directly downwards towards the center of the Earth. But let's shift that back to the perpendicular direction. Also, we have this force from the wind. So it all acts in the same direction. We know the hypotenuse and we need the opposite. So we're going to use sine now. So sine 15 is equal to the opposite divided by 27 newtons. So the opposite, sine 15 times 27, which gives 6.988 newtons. That is the force of the post. Then we work out the moment. The distance is 2 meters away from the pivot. So the moment in that direction is 6.988 newtons times 2, which is 13.976 Newton meters. So if there's no wind at this point, we've now got obviously a very large moment, resultant moment going backwards, so that the hoop is going to stand upright. And this is what you're going to expect, but we're told we have a wind. So our moment of the post is 13.976. So if you add these together, the moment of the post plus the moment of the wind, that's going to equal the moment of the base. So 13.976 plus the moment from the wind gives 378.16 Newton meters. So the moment from the wind has to be 364.184 Newton. So we have our moment from the wind, 364.184 Newton meters, and we know that the moment is going to be the distance from the pivots, that's 2 meters to the center of mass of the post arrangement, plus the 0.4 meters, because this is where we're told the force of the wind is acting. So our moment is the force 2 plus 0.4 meters times the force. Oops. So that gives 2.4 times the force. And so this gives us a force of 151.743 newtons in order to make these balanced. Okay? But we need to resolve this to the angle of the wind. Again, we're working in perpendicular at the moment. The wind is not working perpendicularly. So there we go, force of the wind. Let's work out this angle. We know the adjacent. We're now looking for the hypotenuse. So again, we're going to use cos. So the hypotenuse is going to be 151.743 newtons divided by cos 15, and that's going to give 157.096 newtons. So the minimum force needed is just greater than 157 newtons. Now, if you give justify that in your answer, or if you just give, let's say, you can say therefore it just needs to be 157.1 or greater, that's going to give you the mark. So there you go. Okay, let's have a very quick look then at couples and torque. A couple is a pair of moments normally acting in opposite directions. Torque is the turning effect of the two or more forces. So when you have a couple working in opposite directions, you will have a turning force. Let's look at this airplane propeller as an example. You have two forces essentially spinning this thing around. They're both acting in the opposite directions. So you have torque, you have a turning effect. And the couple there is twice force times distance, because they're the same sized force and the same distance away from the pivot. All right, thank you very much for watching. Like and subscribe, please. Next video, part 3, we're going to be looking at the SUVAT equations. We're going to be looking at projectiles, which is always fun. Loads and loads of fun calculations there. For those of you in my year 12 group who are watching this, I'm going to put this on show my homework, but what I would like you to do is please to have a look at questions 1 to 5 on page 22 of the AS A-Level Physics textbook. And for the moments, if you could have a look at questions 1 to 4 on page 25, submit those through show my homework as in the usual way. Thanks again. I will see you guys on Friday when I upload part 3. Stay safe, and I'll see you soon.